Afternoon, boys and girls, and welcome to lesson number 6 on technical sciences. Today it's a question and answer session on Newton's laws because this is a topic that we have really focused on for the past week. And this topic, like I have indicated to you, it carries plus minus 32 marks at the end of the year. And therefore, it is a topic that is very, very critical for you to understand. And it also forms the basis of other topics like your momentum and impulse, as well as work, energy, and power. So it is very important for us to understand this topic thoroughly. And hence, we took quite some time to be able to really dwell deep into it and engage further on it and try to understand it. Now, I hope you have questions that you have already sent in from yesterday, or you will be able to send them through today. And the email that you can use to send your questions is this one: stemdigitalschool@africateengeeks.co.za. From next week, I will be giving you a different email address that you can use to specifically send in technical sciences questions, and you can send them anytime that you want, and I will be able to answer you even outside a specific lesson. So you remember me, I'm Mr. Sibanyoni. Maybe it's the first time that you're tuning in, and I'm responsible for technical sciences. Right. Now, today we are going to look at these Newton's laws. We will review it, but we will review it using questions from previous examination papers, and we will be doing integration again of these laws. So I've chosen questions that integrate all these laws in one question, and then we'll do diagnostic errors, meaning some of the mistakes that you do as a learner, and tips as to how to rectify that. And we will be doing questions from November 2018 question paper as well as 2019 question paper. And then I will just make a few statements there just to conclude this particular topic. So without any waste of time, we are going to then look at question number 2, which was from last year's question paper, November 2019. And it was question number 2, and it was on Newton's laws of motion. And question number 2, it was based on a single object that was on a horizontal plane. Now let us read the question. The question says, a toolbox with a mass of 45 kilograms rests on a horizontal rough surface. Gary pulls the toolbox with a force of 120 newtons at an angle of 60 degrees to the horizontal using a rope as shown in the diagram below. The toolbox is not moving as he is pulling it. So there we are given a diagram of the toolbox, and we can see the mass is 45 kilogram, corresponds to what has been written there. And here is a force of 120 newtons that Gary is applying using a rope, and he's applying the force at an angle of 60 degrees to the horizontal. Now, The first question there, it says to us, draw a free body diagram of all the forces acting on the toolbox. Now, if I want all the forces that are acting on the toolbox, remember, we definitely draw for ourselves a free body diagram. Now, this is how our free body diagram is going to look like. Number one, we have the force of gravity that is going downwards. And then we have the normal force that is going upwards. Now, why do we have the normal force? Because the object is on the ground. It is on a surface. So we have a normal force that is acting upwards. Then the other force that exists is the force that Gary is applying, right? And remember, it makes an angle of 60 degrees with the horizontal. The other force that the object is experiencing is frictional force. And here, it is very clear that that frictional force is the static frictional force. Now, what we need to understand is it was at rest. So if it is at rest, the friction that is experienced is the static frictional force. Are we clear, my dear learners? Is the static frictional force. And hence there, it was very clear that the type of force is your static friction. But also, some of the labels that we can apply there or we can use is FF. In other words, just frictional force, even if you don't specify the type of force that the object is experiencing. So even if you don't state that it is static friction and you just say it is frictional force, that is correct. Or if you just say F for frictional force, it is correct. Or static friction, which is Fs, it is correct. Now, another symbol that you can use there for force of gravity, remember it's weight. But weight is a small letter W. But it is always best for you to get used to talking about Fg, the force of gravity. Because even in your formula sheet, it's written there as Fg is equal to mg. Now, how do we allocate marks here? Remember, the mark is for the force, is for the arrow touching the dot, because we represent the object as the dot. So it is for the arrow touching the dot and also the arrowhead and the correct label of the force. So there it's written F subscript N. In other words, it's a force and specifically is the normal force. But remember some of the labels that you can use, right? You can also just write capital letter N. That is what most of you are used to represent our normal force. And then the other force is the force of Gary. Another learner could have said, this is F, capital letter F, to show that it's a force that is applied, or F, A, that A stands for applied. So it means it's a force and it's definitely an applied force. And there's more that you can use. Other labels that are also acceptable is when you write it in full. Instead of saying FA, a learner can actually say F applied, meaning you can write that applied in full. That will carry a mark. Remember again, this force is making an angle of 60 degrees with the horizontal, so you will draw it exactly like that. And it must touch the dot, it must have an arrowhead, it must have a correct label, and that will give you a mark. And the same applies to the force of gravity, and the same applies to your frictional force, in this case, the static friction. Now, my dear learners, this method here It's actually not how we draw a free body diagram, because everything is the same except, or rather, let's check it like this: the normal force, there it is. The force of gravity, there it is. It's the same. The static frictional force, the static frictional force, there it is. But now in this diagram, they took the force that Gary is applying, because it was acting at an angle to the horizontal, an angle of 60 degrees to the horizontal. Then they broke it into components. In other words, when you are pulling an object at an angle of 60 degrees like this, you are actually pulling it to the right. At the same time, you are also pulling it upwards. So when you have a force and you are applying it at an angle, then it's similar to just saying you are pulling it to the right. At the same time, you are pulling it upwards. And those represent the components of this force. So to the right will be the horizontal component, upwards will be the vertical component. So sometimes, instead of showing this force like this, then the force is shown in terms of its components. But this method, it's simply for when you want to perform calculations. The free body diagram that we want is this one: 1, 2, 3, 4, which represents the exact number of forces that are acting on that object, and not this one. So this is just an option that was accepted. Now, the fact that it was accepted in 2019 does not mean that it will be accepted in 2020. So stick to this: the forces exactly as they act. So the force of Gary exactly as it acts at an angle of 60 degrees. Though in your rough work, this is going to be important, because you will need to be able to calculate or use the magnitude of the vertical component of the force and the horizontal component of the force to perform calculations. But the free body diagram that we want is this one and not this one. We don't really want you to break it into components on there. Don't break it into components. You only break it into components when you are performing your calculations, but the free body diagram will be like this, right? So that is that altogether, my dear learners. Now, they tell us we need to state a law of motion that can be used to explain why the toolbox is not moving. So we need to be able to state the law. Now, before we can do that, let us think about why the toolbox is not moving. Because if we know why the toolbox is not moving, we will then be able to associate it with a specific Newton's law of motion. Now, there you have a toolbox, and it rests on a horizontal rough surface. And Gary comes and pulls it again with a force of 120 newtons. But when Gary pulls it with a force of 120 newtons, the toolbox is not moving as he is pulling it. And the question is, why is this toolbox actually not moving? And we know if an object is at rest, and it remains at rest, it means the net force that is acting on this object is 0 newtons. So the net force here is 0. And if the net force is 0, remember, it does not mean the forces are not being applied. There are forces that are being applied, but these forces are balanced. And if the forces are balanced, it means that the net force is 0. And if the net force is 0, the object is not going to accelerate. The object will remain at rest because the net force that is acting on the object is 0. That is the explanation of why this object is not moving. I mean, if Gary pulled this object and this object started to move, and perhaps this object started to accelerate, then we would know the net force is greater than 0. But here, the object is at rest. They pull it, Gary pulls it, and it still remains at rest. It means the net force acting on the object is 0. So the object will remain at rest even when he pulls it, only when the net force is 0. So when the forces are balanced. Now, which law is relevant here? Now, the law that is relevant is Newton's first law of motion. Now, we have correctly identified that the law here is Newton's first law of motion. But the question did not say we must write down the name of the law. The question says we need to state the law of motion that can be used to explain why the toolbox is not moving. Now, because we have identified that it's Newton's first law of motion, we are now required to state it. And I want to show you how we mark, because now there are critical words that must be there. There are words that you cannot omit, because if you omit them, then we lose the scientific meaning. And we know the law states an object will remain at rest or continue moving at a constant velocity. So that carries 1 mark. Unless a non-zero net force acts on it. In other words, this object is at rest, so it remains at rest. Why? Because the net force acting on it is 0. But if it was not 0, if it was a non-zero net force, then it will not remain at rest. So the object is remaining at rest because the net force acting on it is 0. Right, so you need to understand that. Now, be able to state it. I mean, if you omit the word there, constant velocity, you would lose marks. If you omitted the word rest, you would lose marks. If you omitted the word or the phrase will remain, you would lose marks because it would lose the scientific meaning. So we know an object will remain at rest or continue moving at a constant velocity unless a non-zero net force acts on it. Then they ask us, use the law in question 2.2 to explain why the box is not moving. Now think about this. We've already alluded to that, and we are saying it is at rest. They pull it, it still remains at rest. It is because the net force that is acting on it is a 0, right? All the forces are balanced. And when all the forces are balanced, it means your net force is 0 newtons. So there, how we allocate marks is to say it will remain at rest because the net force acting on it is 0. and that is why it will remain at rest. And that is essentially what Newton's first law of motion is saying. Now, let us look at some of the mistakes that you as learners make. You see, in this question, most learners did not state Newton's first law of motion because they could not relate the given situation to the law. So they could not actually see that an object is remaining at rest and continues to remain at rest even after being pulled because the net force acting on it is zero. So most learners really could not do that. And the reason some of the learners will not be able to do that is because you do not analyze the scenario first. You must be able to analyze the scenario first and pick up, on words that give you meaning. For example, the horizontal rough surface, the rough that tells you that there is frictional force. So you need to be able to do that, analyze what is happening, and be able to make your predictions. Furthermore, those who could identify that Newton's first law was involved gave the name of the law instead of stating it. Now, the question was very clear. You need to state the law, and that's what I said to you before. They didn't say give the name of the law. They said you must state the law. So, after correctly identifying the law, then you just state the law. Then some learners there were learners who actually gave the name of the law instead of stating it, and some of the learners who were able to state it, they omitted keywords like uniform velocity, which is constant velocity, and they also omitted resultant force, meaning the net force. So be able to do that, and hence I have actually shown you here that this is how we mark. You cannot omit those keywords because you will lose marks. It changes the scientific meaning. Then we were supposed to use the law to explain why the object is not moving. Now, some of the mistakes that the learners do is that they could not use the law to explain the situation as required by the question. Instead, they simply stated the law. The question required the explanation applying Newton's first law to say why the toolbox is not moving. Now, what I also want you to see is that these questions are interrelated, 2.2 and 2.3. And if you are not able to pick up what is going on here, then you are definitely going to forfeit the mark on 2.3. So be able to work with your laws. Right. Now, let us go to this question. It's still a question on Newton's laws of motion, but this one is from November 2018. And this is question number 2. Now here we have Sipho and Jerry, and they are pulling a log of mass 35 kilograms across a rough horizontal surface. Immediately when they say rough to us, we underline that, and we know that rough means that there is a frictional force that is acting on the object, on this log. Now, Sipho is applying a force of 30 newtons to the west. And we can see that. In other words, my dear learners, when we start to talk about direction here, we will not be talking left and right. And the reason is because they have directed us there that we have west. It means we'll talk about west and east, north and south, if there's a need to talk about north and south. But you can't talk about left and right. You will forfeit marks because they told us that direction is west. While Jerry applies a force of 150 newtons at an angle of 60 degrees to the horizontal, as shown in the diagram below. So this force that Jerry is applying is making an angle of 60 degrees to the horizontal. Then the log experiences a frictional force of 5 newtons to the west. Now, we've been given the magnitude of the frictional force, and we definitely know that the frictional force exists because they said the surface is a rough horizontal surface. Now, we are required to define the term net force. Now, we've been defining this one all over the week, and the definition is there in your examination guidelines, and it is for 2 marks. Now, let us see how do we mark this definition as well. We say a net force is a single force that has the same effect as 2 or more forces acting together. Now, why do we say that? Remember, merely just reading a definition is not really going to help you if you don't understand it. So, when there are many forces acting on an object, there is an ultimate force that the object is actually feeling. The ultimate force that the object is experiencing. So because of all the forces that are acting in all the different directions with all the different magnitudes of those forces, and when these forces are acting together, they form, or rather, they make the object to experience a net force, a resultant force. And that force, which is the net force, it has to do with the combination of all the forces acting on the object in their different magnitudes and in their different directions. So the forces that could be acting could be 2 or more forces acting together. Or simply, it is the vector sum of all the forces acting on an object. So that is when you will be taking all the forces acting on an object and you will add them. And when you add them based on their different directions. And hence, we say it is the vector sum of all the forces acting on an object. So be able to know that. You can see those words that are underlined, they are critical. You omit them, you lose marks. 2 or more forces acting together, you make omissions there, you lose marks. So be able to work on that. Then on the same question, we are required to determine the magnitude and direction of the net force that is acting on the log. So we must get the net force of all the forces that are acting on the object. Now, my dear learners, what are the forces that are acting on the object? Number 1, we have the force of gravity that is going downwards. Then this log is on a surface. So we have the normal force acting on the object and it is going upwards. Then we have the frictional force acting on the object, right? Because it's on a rough horizontal surface and that force is 5 newtons. So it is going in that direction to the west. Rather, instead of left, it's going west. Then we have the force that SIPO is applying in the westerly direction, which is 30 newtons. And we have the force that Jerry is applying of 150 newtons at an angle of 60 degrees to the horizontal. So in total, we have 5 forces. It is the force of gravity downwards, the normal force upwards, the force that SIPO is applying, the frictional force acting on the object, and the force that Jerry is applying. So there we have 5 forces that are acting on the object. Now, these forces that are acting on the object, we know all the forces that are all the forces that are vertical, we know they are balanced because my object is not moving up and down. But now, because my object is moving horizontally, then I know all the forces that are acting horizontally, they are not balanced. Now, what are the forces that are acting horizontally? The forces that are acting horizontally is the force that SIPO is applying, which is 30 newtons to the left. It is the frictional force acting rather to the west and not left. In the western direction, the frictional force. Then you look at this one and the question is it acting vertically or is it acting horizontally? And the question is, it has components and one component is acting vertically upwards and one component is acting horizontally in the easterly direction. Similar to the question that we did, it means we can break this force into components because when it is at an angle of 60 degrees to the horizontal like this, we won't be able to work with it. So it is better to break it into components. So when we break it into components, we'll have the vertical component going upwards and the horizontal component that is going in the easterly direction. In other words, to determine my net force, I'm only going to look at the frictional force of 5 newtons west, the force that SIPO is applying west. I'm also going to look at the horizontal component of that force because I'm only interested in the horizontal forces. And I will do the vector sum of all these forces that will be acting horizontally, and that will be giving me the net force. I won't be looking at all the forces that are acting vertically because they already give me a net force of 0. So to calculate that, we will say the net force is equal to the force, rather the horizontal component of Jerry's force plus the force that SIPO is applying plus the frictional force. And why am I doing that? Because these are the only forces that are acting horizontally. So this one, F Jerry cos theta, represents the horizontal component of Jerry's force. This one represents the force that SIPO is applying. This represents the frictional force that the object is experiencing. Now, to calculate the horizontal component of Jerry's force, we use that formula that we normally use for the horizontal component. And we all know, hopefully so, that the horizontal component of this force will be given by F cos of theta. So if I just want the component of this force, the horizontal component, it will be the force applied multiplied by the cos of theta. Had I wanted the vertical component, it would have been the force that Jerry applies multiplied by the sine of theta. But because I want the horizontal component of this one, it will be the force applied multiplied by the cos of 60 degrees. So the horizontal component will be the F applied is 150 multiplied by the cos of 60. Now remember, this is the vector sum of all the forces acting on the object. So the vector sum means we need to take direction into consideration. To take direction into consideration, let us say we take the east as positive. In other words, the west is going to be negative. And this is exactly what I was telling you, that you cannot talk about left and right, because we've been given a directive there that Zippo was actually applying the force in the westerly direction. Now, this one that Jerry was applying, the horizontal component was going east, hence it's substituted as a positive value. Plus, remember what this plus means. It comes from originally the formula there to say we are doing the vector sum. So it's plus, then we add another horizontal force, is the force that Sipo was applying. It's 30 newtons, but remember it is acting west, so west is negative, plus the frictional force. The frictional force is 5 newtons. And in which direction is it going? It is going in the western direction, so it is negative. Then 150 multiplied by the cos of 60, it's 75 newtons. Positive times negative gives me negative 30. Positive times negative gives me negative 5. So to calculate the net force there, it will give me a magnitude of 40 newtons. And because it's a positive value, then we will say to the east. So the net force is 40 newtons to the east. Now, this is what I also want you to look into. You see, the question was clear. Determine the magnitude and direction of the net force. If they said determine the magnitude of the net force, would just give us the magnitude. If they say to you, determine the net force, and they don't specify direction, the fact that they just determine the net force acting on the object, rather on the log, then you must know that most definitely they must be wanting the magnitude and the direction, because net force is a vector quantity. Right, and hence we've given there 40 newtons, and because it was positive and we chose east as positive, it means our net force is 40 newtons to the east. So 1 mark for the formula of net force in this case, another mark for getting the horizontal component of Jerry's force, then another mark for the forces that are acting in the westerly direction, and 1 mark for both the magnitude of the net force as well as the direction. Now, that gives you a total of 4 marks. Then we are required to state Newton's second law of motion in words. Now that one, we've done it extensively and I hope you know it by now. We say, when a net force is applied to an object of mass m, remember, we apply a net force and we apply to an object of mass m. Then we say it accelerates in the direction of the net force. It accelerates the object in the direction of the net force. And remember, you must write it in full. This acceleration is directly proportional to the net force and inversely proportional to the mass of the object. So this whole from there up to there is the first part of the law. From there up to there is the second part of the law, and you must write it as it is altogether. So be able to work with this, because I know some of you in your textbooks, it ends there, but that's not the full Newton's second law of motion, because it has actually omitted the relationship of acceleration with the net force. So we start there. When a net force is applied to an object of mass m, it accelerates the object in the direction of the net force. And we know that when there is a net force acting on an object, the object will definitely accelerate, and it will definitely accelerate in the direction of the net force. And again, we know acceleration has a direct proportionality relationship with net force. Again, acceleration has an inverse proportionality relationship to the mass of the object. Right. Then, question 2.1.4, we are required to draw a free body diagram of all the forces that are acting on the log. Right. Here are the forces. The first force is the force of gravity. Right? You remember that. The next force is the normal force because the object was on a surface. The other force is the applied force that Jerry was applying at an angle of 60 degrees to the horizontal. The other force was the frictional force. Remember that one that the object was experiencing of 5 newtons, and the other force was the force that Sipo was applying. Remember now, how do we give a mark? We give a mark if the arrow is touching the dot and the tip of the arrow is drawn directly where the line of the arrow ends, and you have a correct label. Remember, another symbol we can use for the normal force is capital letter N without actually showing the F. F Jerry, we can also call it F applied or F capital letter A because it's the applied force. Force of gravity, force, and small g for gravity, right? And then FCPO is also the applied force. FF, that is your frictional force. Remember what I said about this one, my dear learners, is that we don't actually want this diagram, and that is why it's option 2. It's actually not an option because we are not really accepting this. Are we clear, my dear learners? And for one reason, because we want the force to be shown exactly as it acts, as it was acting at an angle of 60 degrees. So what actually happened here is that this force that was applied by Jerry, it was broken into components. So it was broken into the vertical component going up, and it was broken again into the horizontal component. It means the vertical component of Jerry's force and the horizontal component of Jerry's force actually represent that. Are we clear, my dear learners? So this is only needed when you are performing calculations, but when we want a free body diagram, you have to draw it like this. Right. Then the next question says we must calculate the acceleration of the log. Now, to calculate the acceleration of the log, we will definitely use Newton's second law of motion equation. Now, what you must remember is that we had already calculated the net force that is acting on the object in question 2.1.2. So when we have a net force of 40, then we definitely are going to have acceleration because the net force causes the object to accelerate. So we don't need to go back and actually calculate the net force. We can actually just go and substitute it as 40 because this was the net force on the log. And we'll substitute it with a positive value. Why? Because the net force was in the direction to the east. So we'll say net force is equal to MA. Remember, the net force is made up of all those horizontal forces that are causing the horizontal acceleration, which is your net force. And we calculated it and we found it to be 40. And because the net force was to the east, and the east was positive, then we choose east as positive, and therefore the value will be substituted as 40. And the mass of the log is 35 multiplied by acceleration. Therefore, acceleration is equal to 1,14 meters per second squared. Remember, with acceleration, the units are meters per second squared. And what you need to also remember is that you must have a dot there. Some of the learners will be writing ms to the negative 2, right? That is incorrect. It must be meter per second squared. So the dot must be there. And to say per means that it is a negative power. So it's meters per second squared. And that is where we get our 3 marks. 1 mark for the formula, 1 mark for the correct substitution, and 1 mark for the acceleration. Are we together? Then we move to question 2.2. Now, question 2.2, right, sorry about that. Question 2.2, it's now part of question 2, but it speaks to a different scenario. Now, it says, the photograph below shows a construction manager's car hitting a wall. So this is a construction manager's car and it hits a wall. That is so unfortunate, right? The car was moving at a velocity of 120 kilometers per hour during the time of the accident. A passenger in the back seat who was not wearing a safety belt hit the dashboard and suffered head injuries. Then they asked us to state, or rather to explain or to say which Newton's law can be used to explain what happened to the passenger. Now, I'm going to just give you a minute to think about what is happening, take note, and tell me which of the 3 Newton's laws of motion, be it Newton's first law of motion, second law of motion, or third law of motion, that we can use to explain why the passenger actually hit the dashboard and suffered head injuries. Which law can we use? Remember once again, learners, that you are free to definitely send in questions to questions@africateamgeeks.co.za, and I will be able to answer your questions during this session. Right. Right there, I actually gave you more than a minute. Now, if you remember, Newton's first law of motion, sometimes it can be referred to as the law of inertia. Now, my dear learners, you will remember that when we define the term inertia, we say it is the property of a body to resist any change in its state of motion or rest. The property of a body to resist any change in its state of motion or rest. Now, if an object resists any change in its state of motion or rest, we say it has inertia. Now, the state of motion of the passenger was actually moving forward. So when the crash occurs, the passenger's body wants to continue to move forward. And that is exactly what happened, because the passenger's body was moving at 120 kilometers per hour forward. So when the collision took place, the body resisted to change going forward, and hence it kept on going forward because it resisted any change in its state of motion. It's as if it says, I want to continue moving forward, so I'm going to resist any change that is going to occur, and hence the body continued to go forward. It is because of the inertia of a body, because it wanted to continue moving forward. And because it has to do with inertia, and we know inertia, it has to do with Newton's first law of motion. So the question there said, which Newton's law can be used to explain what happened to the passenger? So most definitely the answer to that is that it is Newton's first law of motion. Then the next question says, state the law mentioned in question 2.2.1. Now, these two questions are interrelated. If you could not identify the law there, then you would not be able to state it. And to state it, put simply, we know this: an object continues in a state of rest or uniform velocity unless it is acted upon by an unbalanced force or a net force or a resultant force, or what we refer to as a non-zero net force. It all means the same thing. So there, what you should be able to see is that there are keywords and they are underlined, so you cannot omit any of the words there altogether. Right, put in a different way but meaning the same thing: an object will remain in its state of rest or continue with a constant, or continue moving with a constant velocity unless it is acted upon by a resultant force, an unbalanced force, or what we definitely refer to as a non-zero net force. Right. Use the law stated above to explain what happened to the passenger. Now, we know the passenger was definitely moving at 120 kilometers per hour. How do we know that? Because the passenger will move at the same velocity as the car. So when the car hit the wall, bringing a change in the state of motion of the passenger's body. Now, what does that mean? Because now the driver, rather the passenger, was moving forward. So when the car collides with the wall, there is a force that the wall applies on the car, which is a backward force, right? There is a backward force. So the backward force is actually trying to change the state of motion of the body. But what happened? The passenger's body continued to move forward. Why did it continue to move forward? Because it was resisting to change its state of motion of going forward. And hence there we say the body resisted the change in its state of motion and continued to move at 120 kilometers per hour, meaning it continued to move forward. And then what happened? The dashboard exerted a net force that stopped the passenger, because they told us there that he will hit the dashboard and suffered head injuries. So why did he suffer these head injuries? Because when he hits the wall, he exerts a force on the wall. When he hits the dashboard will also exert a force on him, and that is why he suffered injuries. So if the force that is exerted on the dashboard is the forward force, then the force that is exerted by the dashboard on the passenger is a backward force. So that is essentially what this force is, rather what actually happened to the passenger. So he hit the wall, right? The car hit the wall, and that brings a change in its state of motion of the passenger's body, right? Why? Because when the car definitely hits the wall, there's a force that is exerted on the car, and that tries to bring a change in the state of motion of the passenger. But the body will then resist changing that state of motion, and it continues to move forward at that velocity of 120 kilometers per hour. Now, as the body resists changing that state of motion, and in turn, he continues to go forward. When he hits the dashboard, he will exert a force on the dashboard, but the dashboard will simultaneously exert a force on the passenger. So that will stop the passenger at the time, and because it's a force being exerted on the passenger, then you will find that the passenger is definitely going to suffer injuries. Right. Now, let us make a conclusion here based on what we have learned in this particular topic, is that the laws are interrelated. The questions are going to have parts of Newton's first law of motion, a big chunk of Newton's second law of motion equations, Newton's second law of motion, where you apply the equation, where you draw free body diagrams as well. And also it will integrate Newton's third law of motion. Why? Because when we deal with objects, there is an interaction between them and they exert forces on each other. And hence we need to integrate the three Newton's laws. So let us be able to apply and integrate the three Newton's laws of motion. Now, my dear learners, what you also need to understand is that you have been given examination guidelines. And these examination guidelines, my dear learners, they are made to help you, right, in preparing for your examination. And they will definitely help you if you are using them. That is where you will be getting your principles, right? That is where you will be getting your laws. That is where you will be getting your definitions as well. And you need to state them as they are in the examination guidelines. Now, if you don't do it in that particular fashion, if you don't state the laws as they are, if you don't state the definitions as they are, then you're going to forfeit marks, because most of the time you tend to omit the keywords that change the meaning of the definition or the meaning of the principle. So it is critical that you use your examination guidelines at all material times. Furthermore, my dear learners, what you need to understand is you must be able to do everything that is stated on the examination guidelines with regards to the topic at hand. So you must be able to check, what do I need to know for Newton's first law of motion? What do I need to know for Newton's second law of motion? And what do I need to know for Newton's third law of motion? So be able to work with all of that. Right. Now, just check there from your examination guidelines. This is what you need to know with regards to Newton's first law of motion. Right. There we go. Under these Newton's laws and application of Newton's laws, remember you must be able to describe what weight is, which is your gravitational force. You must be able to calculate weight as W is equal to mg, but remember you are going to get a formula sheet that says Fg is equal to mg. You must be able to define what the normal force is, be able to define what the frictional force is, be able to differentiate between static friction and kinetic friction, be able to define what tension is. Remember, tension is that force that acts on a rope or a string. Be able to distinguish between mass and weight. Remember, mass is measured in kilograms, but weight is measured in newtons, because weight is the force of gravity. Be able to resolve an applied force into components when it is acting at a particular angle. Again, for free body diagrams, be able to define free body diagrams, be able to draw a free body diagram, and be able to determine the net force when two or more forces are acting on an object. Again, be able to state the laws, the first law, the second law, the third law, be able to define inertia, be able to define mass, give examples to illustrate Newton's first law. We did that in our first lesson. Discuss why it is important to wear seat belts using Newton's first law. Be able to define acceleration. We talked about this. You need to be able to state Newton's second law of motion. Be able to use F net is equal to ma, the Newton's second law equations. But remember, you don't do pulley problems and lift problems. And be able to apply these laws to a variety of questions. And for questions where your net force is zero, meaning the forces are at equilibrium, and also where the net force is greater than zero, meaning non-equilibrium problems, be able to deal with these laws in an object that is moving in a horizontal plane with friction and without friction, as well as in a vertical plane for a single object, and also be able to deal with two objects, a two-body system, where they are connected by a light inextensible string, both on a flat horizontal plane with as well as without friction. Remember, here we are likely to ask you to calculate the acceleration of the system, of the objects in that system and also the tension. Be able to identify, rather to state Newton's third law of motion, and as well, given a scenario or a question, you must be able to identify action-reaction pair of forces and be able to list those properties of action-reaction pair of forces. You will remember that those properties are the fact that the magnitude of the forces are equal, but it acts in opposite direction to each other, and that those forces act on two different objects. So that is that, my dear learners, in terms of Newton's laws of motion. In our next lesson on Monday, we are definitely starting with momentum and impulse. Right, I see you haven't sent in any questions as yet. Please send in those questions to that email that I gave you, questions@africateamgeeks.co.za. So that I'm able to assist you. So this is going to mark the end of our lesson today, and I hope that you have learned a lot in this particular topic, and I will definitely see you on Monday. Thank you very much and enjoy the rest of the afternoon.